Let's start at the very beginning. A very good place to start by looking at some basic chemical concepts. Describe different substances using properties. We can divide properties into intensive properties and extensive properties. Intensive properties are properties of a substance that do not depend on the quantity of a substance. These are things that are intensive to the object's being. I like to think of it as intrinsic, your intrinsic value, the intrinsic properties, but we say it's intensive. The intensive properties, examples of intensive properties are color, right? Regardless of how much of a substance you have, it's the same color. Density, right? Density is the amount of mass per a unit of volume, and that's the same regardless, since it's a ratio, right? It's a ratio, so it's the same regardless of how much you have. Whether or not something catches on fire is independent of how much of it you have. So flammability is an intrinsic property, so is luster, which is a fancy way of saying shiny. Temperature and conductivity are all examples of intensive properties. Extensive properties are properties of a substance that depend on the quantity of a substance present. In other words, the descriptor for a substance's extensive properties would change depending on the quantity. Mass changes depending on how much you have, volume changes on how much you have, and the amount of heat given off during a change depends on how much you have. So those would all be examples of extensive properties. We can also divide properties into physical properties and chemical properties. A physical property is anything about a substance that you can observe without changing the chemical identity of a substance. Color is an example of a physical property. You don't have to change a substance in any way to know what its color is. Same for temperature. You don't have to change a substance in order to know its temperature. Density, translucent, whether or not something's translucent or opaque, or luster are all examples of physical properties. Now you're saying, wait a second, some of these physical properties were also intrinsic properties. You're right. They can be both. So these are all examples of physical properties. Why don't you write down Steve McNair? Write down Steve McNair. Everybody write down Steve McNair. In addition to having physical properties, you can also have physical changes. A physical change is any change in a physical property that does not change the chemical identity of a substance. The classic examples of a physical change are phase changes. Boiling, freezing, melting, condensation, sublimation. All those are classic examples of a physical change. Let's take a simple one. Let's take water. We have ice, which is just water, H2O, as a solid. We melt it, and we get liquid water, but liquid water, just like water solid, is still H2O. So chemically, we have the exact same substance at the end of the change as we do at the beginning. The substance is in a different form, but chemically it's the exact same. In other words, no change in the substance identity has occurred. Therefore, it's a physical change. Another example would be shape. I can change the shape of an object without changing what the object is. Pick up a piece of paper, crumple it. You've changed its shape, but you still have a piece of paper. You can take that piece of paper and you can tear it into a million pieces, but you still have paper. That's the same thing that's occurring when we freeze or melt something, right? You boil water, you have your water molecules all close to each other, but when you boil them, You're just tearing them apart. They're still water molecules, but the water molecules are now all spread out in the gas form. So again, you haven't changed the identity. All right, a chemical property is any property that describes how a substance reacts with other substances. My favorite is flammability, which describes how a substance reacts with oxygen. For that matter, so does rusting. Reducing agent describes how an object reacts in a reaction. It wants to donate electrons. Saying something's an acid or a base, again, describes how a substance reacts in a chemical reaction. Those are all examples of chemical properties. A chemical change is any change in which the chemical identity of a substance is different at the end of the change. A chemical change can also be referred to as a chemical reaction. Classic example is combustion. Here's combustion that occurs in our everyday life. We have natural gas, reacting with oxygen to yield carbon dioxide and water. So we've gone from having two substances, natural gas and oxygen, to having two different substances, carbon dioxide and water. Thus our ending substances are different from our beginning substances, which is what a chemical change is. Any change that involves changing the identity of a substance. Another classic example of a chemical change is digestion. Food goes in your mouth and comes out in a very different form. Why don't you write down Vince Young? Write down Vince Young. V-I-N-C-E, and then last name Young, Y-O-U-N-G. All right, which of the following are chemical changes? Let's see, a plant converting carbon dioxide and water to glucose. Well, we're starting with carbon dioxide and water, and we're ending with a different substance, glucose. So our starting substances are different than our ending substances. So it's a chemical change. Dry ice sublimating. In case you're unfamiliar with the term sublimating, sublimating is when a substance goes from a solid straight to a gas. And the classic example of something sublimating is dry ice, or something you may actually have around the house. Mothballs, right? Mothballs are solids, and you put them in your drawer, and a couple months later they're gone. What happened to them? They went straight to the gas form. They sublimated. Okay, so is sublimation a physical or a chemical process? It's a physical process. With our example of dry ice, in dry ice you have carbon dioxide as a solid going to carbon dioxide as a gas. But either way, it's still carbon dioxide. So it's a physical change. Making a vodka martini. When you make a vodka martini, shaken of course, not stirred, you're mixing ethanol and water together. Ethanol is the fancy name for drinking alcohol. Is the drinking alcohol still present after you mix it with the water? Yeah, it is, right? Otherwise it would defeat the purpose of making the martini. Therefore, mixing two things is a physical change. Dissolving something and dissolve in something else is also a physical change. One that I haven't gone over with you yet is the classic example of making salt water. If I have some salt and I place it in water to dissolve it, is my salt still there? If you place salt in water and you drink the water, can you taste the salt? Yeah, so it still has to be there. Therefore, when you place salt in water, you get wet salt. It's still salt. So it's a physical process. dissolving is. And I got that from the Otis School of Public Speaking. All right. Lava hardening. You go from liquid lava to solid lava. Yep, you got it. That's a physical change. A wick burning. What happens when you burn a wick? You change it into carbon dioxide and water, actually, water vapor. You're actually changing what a wick is. So since you're changing what the wick is, it's going to be a chemical change. Now, you're burning a wick and it's melting the candle wax. So you're going from solid wax to liquid wax, but it's still wax. So therefore, the melting of the candle itself is a physical change. Gasoline in your car combusting. When you drive your car, you're actually setting gasoline on fire inside your engine. You're converting gasoline into carbon dioxide and water. So you're going from having octane to carbon dioxide and water. You're changing substances, making combusting gasoline a chemical change. Baking a cake. You bake a cake and you start off with a bunch of goopy liquid. You place it in the oven and what happens? It rises, it becomes light and fluffy. What happens? Where did all those little air pockets come from? During the process of baking a cake, several chemical changes occur. But one of them actually produces carbon dioxide, which is what makes your cake nice and fluffy. As the yeast eat the actual sugar and starches in your cake, they poof out carbon dioxide into your cake batter, which causes it to rise. Rise! Rise! Whoa! So that's a chemical change too. Electroconductivity. We run electricity through copper wire. After we run electricity through copper wires, the copper wire is still copper wire? Yeah, it's still copper wire. Therefore, it's not even really a physical change. It's more of a physical property. Why don't you write down Matthew Hasselbach, or just make it Matt Hasselbach. Hasselbach. And I probably misspelled his last name, but Hasselbach. All right, let's talk about chemical and physical properties. Chemical and physical properties are really important to chemists. We can use them to identify unknown substances. There is a whole field of chemistry devoted to the study of unknown substances, and that's the field of analytical chemists. And let me tell you, all the cool chemists are analytical chemists. I say totally unbiasedly. Now, let's start with two things we can find lying around the house. Ordinary packing peanuts. There are actually two types of ordinary packing peanuts. One's made of styrofoam and one's made of starch. Now, the texture and feel, which are physical properties of these two substances, helps you tell them apart. But another way you can tell them apart is by how they behave when you place them in water. Styrofoam does not dissolve in water, right? I've got my styrofoam packing peanut in my beaker there, and it's just floating along, right? Whee! The good ship styrofoam packing peanut. Nothing happened to it when I placed it in water. Starch packing peanuts, however, do dissolve in water. I place my starch packing peanut in my water, and what's happening? Voila! It dissolves, right? So I can use the physical property of dissolving to actually help me differentiate between my starch packing peanut and my styrofoam packing peanut, which just floats merrily on top of the water. If I can manage. Now you see why Rick Pitino doesn't return my phone calls. But you can see that the styrofoam packing peanut doesn't dissolve in water, but my cornstarch one did. Alright, so let's refill our water here. Now sometimes physical properties alone aren't enough. I have two clear liquids here. On the face of them, they would both look like water. One of the reasons it's always important to label containers in a chemistry lab. They both look like water, but one of them is not. We said our styrofoam packing peanut does nothing when you place it in water. If we take our styrofoam packing peanut over to our other container, though, I'm gloving up. The excitement as we watch Dr. Kelly put on a glove. Oh wow, fingers in the glove. All right, now we got fingers in the glove. All right, we take my styrofoam packing peanut and place it in our mystery liquid here. And what happens? What happens? Ta-da! It dissolves, right? So is this substance water? No, obviously not, since my styrofoam reacted with it. So I know there's a difference between these two liquids. Now, my favorite chemical property is flammability. Water's not flammable, so water won't catch on fire. This substance, however, which we've established isn't water, we can reaffirm it's not water by seeing if it'll catch on fire. So I'm going to put a little bit here, and then I'm going to move this container far, far, far away. Close up. All right, let's see if this substance that we poured in our pan here is water. Whoa, is it water? No, it caught on fire. So we know from its chemical properties that it's not water. Now, fire is really useful to chemists because different things burn with different colors. What we see here is we see a nice orange flame caused by the severing of lots of carbon-carbon bonds. And that's the color we're used to seeing fire. Because when we burn things on a camp stove, we're severing lots of carbon-carbon bonds. Not all substances burn with the same color. We can actually use the color produced when something catches fire to help identify it. There's a whole instrumental range of instruments based on this called flame atomic absorption spectroscopy, where basically you shove something in a flame and see what color it gives off. I've got another substance here. Now you have to pay attention to the exact moment this catches on fire. I'm going to move it forward just a little bit here. And if we're lucky, when this catches on fire initially, we're going to see a little bit of the luck of the Irish. Or if I can light a match. Come on, baby. Whoa! See, we've got a nice intense green flame there. So is the substance that we're burning those simple carbon-carbon bonds? No. This substance that we're burning actually contains a great deal of boron, which is producing a nice green flame for us. This is a very common, enjoyable chemistry technique. Matter of fact, there is a holiday every year to celebrate flame atomic absorption, and that's the 4th of July, right? We all go out on the 4th of July, shoot metals up into the sky, and try to guess what metals they are based on the colors that they're giving off, right? Does that look cool? I hope it looks cool. But at any rate, that's it. So we can use chemical and physical properties to help us differentiate between different substances and their identity. I apparently poured a little bit more into the pan than I intended. There we go.